Hello, my name is Stephen McDonald. I am a site reliability engineer at Usabilla by SurveyMonkey. As you can see, a bit about me here. So I initially joined Usabilla in March of 2018 in order to help set up and migrate to new cloud-native infrastructure. And around the start of 2019, I took on the logging component of that architecture, which is what led to the material being discussed here. So our infrastructure is completely running in EC2. We have a wide variety of different instances, both legacy infrastructure and cloud-native infrastructure, and we want to aggregate all of those logs together into the one place. So that's the goal that we're working towards here. And so the first iteration that we built was a fairly standard Fluentd setup. So we had two redundant Fluentd aggregators, with the Fluentd forwarding protocol being used to forward logs from EC2 instances. And we used FluentBit, which is a lightweight C implementation of the Fluentd forwarding protocol to do that from those instances. And then those Fluentd aggregators would, of course, do any filtering, do any rewriting, and end up writing the logs to CloudWatch and Elasticsearch, which is, so we were using CloudWatch for archival and Elasticsearch for easy searching of recent logs. So that's all fairly standard. And it worked well to a point, but we ran into a problem that highlighted quite a few problems throughout the entire log processing pipeline. So what we ran into was, the first thing that went wrong was that our Elasticsearch cluster that we were using turned out to be too small to handle the logs that we were putting into it. So that's a fairly innocuous misconfiguration. It means that the logs can't be written to Elasticsearch, but you would expect that the problem would remain isolated to writing the logs into Elasticsearch. Unfortunately, that led us into a cascading failure where we had a misconfiguration of the Fluentd Elasticsearch plugin, which caused log duplication. So this requires a bit more explanation. It is documented in the Fluentd Elasticsearch plugin that in case of a partial failure from the Elasticsearch API, the failed messages will be re-emitted into the logging pipeline. And the reason for this is there's no way in the Fluentd plugin API for the plugin to tell Fluentd some of these log events were successfully submitted, but others weren't. So it just re-emits them from the beginning of the log processing pipeline. So that was our bad. We hadn't read that bit of the documentation, so we hadn't configured it in that way. But that caused log duplication, which both meant logs were duplicated in CloudWatch, but it also meant that it also placed a whole lot more load on the Fluentd aggregators because they were processing the same messages hundreds and hundreds of times over again, eventually to the point that they were unable to accept new logs from the FluentBit clients, which is now a problem because those logs start backing up in log buffers on the individual instances, and if one of those instances dies, we lose any logs that were not accepted by Fluentd. But that caused even more problems because we ran into a bug in FluentBit where, as the log buffer grows, it creates more files to hold the additional logs, and FluentBit has a bug where it will hold all of those files open at the same time, and when it hits its open file limit, it just crashes. It doesn't gracefully recover from that situation. So that means that logs are not even being collected by FluentBit once it's crashed. But additionally, FluentBit doesn't always recover from that situation at all without manual intervention. There seems to be another bug where if it crashes while the log buffer is in the wrong state, it will spam a whole lot of empty, invalid log messages at Fluentd instead of sending it the actual log messages that are in the buffer, which means there's now no way to recover those log messages without diving into the internal FluentBit buffer format and manually recovering that, which the easiest thing to do is just consider those logs lost and delete the buffer so that it just picks up new logs. So this one tiny misconfiguration in Elasticsearch turned out to cause problems through the entire pipeline, even in CloudWatch where those logs were being duplicated. So we learned a few lessons from this about the way we were doing things. The initial root cause, which was an overload of Elasticsearch, we can easily fix that. So that's just a case of giving Elasticsearch more resources. But we didn't want a problem in one part of the architecture to be able to cause a whole lot of problems elsewhere. Secondly, the misconfiguration of the Elasticsearch Fluentd plugin. It is documented behavior, but it highlights that it's difficult to configure Fluentd plugins for reliability because you can't assume that because this is an output plugin, it's only going to be able to do the function of outputting logs. It has full access to Fluentd's internal APIs, and in this case, it was using them to behave sort of like an input plugin by re-emitting those log events, which is an input plugin's job. FluentBit's crashing highlights that if Fluentd does have availability problems, this can cause problems on every instance on the network that's submitting logs with FluentBit, which is also undesirable. And so the upshot of all these things, the fact that one component can have knock-on effects earlier on, is we need to decouple those somehow. So if it's difficult to configure Fluentd for reliability, and if Fluentd not being reliable causes problems elsewhere, then we must have something in between there. We need to have a buffer that doesn't break when Fluentd goes unavailable. So we came up with a new plan. First of all, we wrote a new tool. Sorry, not yet. First of all, we decided to use Kafka as a central logging buffer. So whenever any logs went from one system to another, they would always go via Kafka. They would never get written directly from one tool to another. Kafka, if you're not familiar with it, is a distributed message broker. It's used in production by a whole lot of companies. It has demonstrated fault tolerance. We're also using it in our application, so we have confidence in that. There are a couple of added benefits to it as well. Consumers may be stopped entirely, which means that if Fluentd breaks entirely for some reason, such as what I just described, it doesn't. Any log producers don't even see that. They just keep writing their logs into Kafka, and when the consumer comes back online, it can reprocess what it missed. Another added benefit is that you can process the same logs twice by two different applications, which makes testing of new configuration very easy. You don't need to roll out a new configuration and find out if it breaks. You can have a testing Fluentd instance that reprocesses the same logs on real data with a new configuration and just see what happens. So given all of these advantages, it seemed like a good fit for a logging buffer, at least for our use case. We also noticed that we only really need half of what FluentBit was doing for us. So what FluentBit does is it takes logs from a variety of sources, puts them into a buffer that it manages internally, and then writes those logs out from that buffer to some destination. In our case, it was a Fluentd instance, but it can also be Kafka or whatever else. But we don't actually need that first part, reading logs from various sources, because all of our machines are running systemd, and systemd has a component called journald that maintains a unified logging buffer to aggregate all of the logs on a particular host. So we already have a log buffer there. Any log exporter that just reads that and writes it into another buffer is providing duplicate functionality. So we only need that second half. We only need something to read from the systemd journal and write those logs into Kafka. And then as a matter of architectural design, we can say anything that logs must log to the journal. And from there, it will be picked up and taken where it needs to go. So that's all well and good. That's the general design that we're going for. What code do we then need to write to make this architecture happen? So the first thing we developed is a tool called Perapera, which is just a silly pun. So Fluentd is a Japanese project, and Perapera is Japanese for fluent, so it's just reversed. We looked into using the existing FluentBit Kafka plugin for this, but what that does, so it uses a library called libRd Kafka, which is a C implementation of the Kafka protocol. And the way libRd Kafka works for performance reasons is when you write a message to it, it puts it into an in-memory buffer, and then once it's aggregated some messages, it'll write a batch to Kafka. the FluentBit Kafka output plugin considers a write successful as soon as libRd Kafka has it in its in-memory buffer. So if FluentBit crashes while there are messages in that buffer, you just lose them. And we didn't want to. We didn't want that behavior. But also, all of the problems that we'd encountered with FluentBit were related to the way that it does buffering. And as we already said, we don't need it to do any buffering because we have a buffer. So we developed Perapera, which is a very simple tool. It doesn't support more than one log input. It doesn't support more than one log output. All it does is read the systemd journal and write everything in it to Kafka with no processing, minimal filtering. The only thing it does is filter out its own messages if you enable debug logging to avoid write amplification. And we also use message pack, which is the same serialization format used by FluentD's native forwarding protocol, because, well, my reasoning was that it would be most likely to give us the best compatibility with FluentD. FluentD can also read JSON messages from Kafka, but we went with message pack. And the only state that Perapera itself keeps is the journal cursor, which is just an address within the journal, the cursor that was last acknowledged by the Kafka broker. So it waits for the broker to acknowledge that something has actually been committed to the Kafka cluster before it says, okay, I've actually written that. So if Perapera crashes, next time it starts up, it starts reading from that last successful write. So barring any bugs, we're guaranteed that no log messages will be lost. The other component then is making FluentD work statelessly. And what I mean by that is if we want to use Kafka as a centralized log buffer, we want FluentD not to keep its own state because it should be using Kafka to persist its state. This is a bit complicated because FluentD has, there are buffered and unbuffered output plugins for FluentD, and the choice of whether a plugin supports buffered or unbuffered mode is up to the plugin author and not the plugin user. If the plugin author supports both, then the plugin user can choose, but most output plugins only choose to support buffered mode for performance reasons. Because if you're reading one log message at a time, you don't want to make one write call for every log message. You want to batch them together. That's not a problem when we're using Kafka as a log buffer because we can batch read from Kafka, but this isn't the way that these plugins were designed to work. So we would have to re-implement every output plugin in FluentD as an unbuffered output plugin in order to do this. But we didn't want to do that, so we didn't. So what we did instead was we wrote one plugin. So there is an existing output plugin for FluentD called Bufferize, which is intended to give a buffer to an output plugin that doesn't support buffering. So it basically wraps another plugin and adds a buffer to it, and that's all it does. We wrote the opposite of that plugin. So we wrote a plugin called Unbufferize, and what that does is it presents itself to FluentD as an unbuffered output plugin, and it presents itself to a wrapped plugin as the FluentD buffer API, so that plugin is tricked into thinking that it's having messages written to it from a buffer when in fact they're coming directly from the FluentD input plugin. And it also, I'm not going to go into too much detail here, it performs chunking of each stream so that you can use chunk keys in strings in the configuration. If you've used FluentD, you'll know why this is useful. If you haven't, it'll take too long to explain. But this only works well when you can batch reads, as I said, which is perfect if you're using Kafka because we can easily batch reads from Kafka. This wouldn't work well with FluentD's forwarding input plugin because that just reads however many messages the client sent it at a time. So if we put that all together, what actually happens within FluentD is the input plugin, the in-Kafka plugin will not commit a read to Kafka, and commit means inform Kafka, yes, I've read these messages, don't send them to me again. The input plugin won't actually do that commit until the emit call, which is the name of the function in FluentD that sends a log event to be processed, returns successfully. Normally, this will return when they've been committed to the buffer within FluentD, within the output plugin. But with the Unbufferize plugin, we made sure that it instead returns once the logs have been written out successfully to their final destination. So we're sure that they're actually on stable storage wherever they're supposed to go before we say to Kafka, yes, I've read these messages. We also made sure that if an exception is raised in any of this code, it does get propagated back to the input plugin and the read is not committed. So any errors will result in a retry of reprocessing those logs. That means that we have at least once rather than at most once delivery, so we can get duplicate logs, but that's better than losing logs, at least for our use case. So here's a diagram of how it all fits together. Instead of FluentBit on the EC2 instance, we have Perapera doing nothing but reading from the journal and writing to Kafka. The Kafka topic is then an intermediary buffer. Kafka is, as I said, highly available. It can easily survive the loss of a node. So Perapera should theoretically never have a problem writing to that. Now that I've said that, we're probably going to have an outage with it, but you get what I mean? So it doesn't break if Fluentd goes down, is the point. Fluentd reads from that Kafka topic and writes to another Kafka topic. And here's the other thing that we can do with this, is we can break up the Fluentd logic into multiple different Fluentd processes. So rather than having one Fluentd that does filtering and also writes to CloudWatch and Elasticsearch, we have another Kafka topic in between the filtering Fluentd and the output Fluentds. And the benefit there is, if we have another outage with Elasticsearch, the only thing that can affect is that one little Fluentd on the bottom right of the diagram. That cannot be propagated any further back through the chain because all that Fluentd is doing is reading from a Kafka topic. The filtering plugin will have no knowledge of this. Log messages will not be duplicated in CloudWatch because it doesn't affect the top right Fluentd, and it definitely doesn't cause any problems at all with Perapera. So putting Kafka in between these sort of roles makes everything a lot more reliable, at least in theory. But how does it work in practice? So we found it worked a lot better than the previous approach. It actually made things faster overall because without the buffer within Fluentd, we were just processing batches from Kafka as soon as they came in. The main pain point for it is now the way the Ruby Kafka library works. It only sends heartbeat messages to Kafka in between processing log batches, which means we can either have nice big log batches and very infrequent heartbeats, so it takes a long time to recover from failure, or we can have short heartbeats so that it recovers quickly from failure, but we have to process really tiny batches of logs and then run into stuff like CloudWatch API limits because we're processing those logs too frequently. So that's a bit annoying. That was also difficult to debug because the Kafka plugin for Fluentd doesn't log messages from the Ruby Kafka library by default. So it took me a while to figure out there are actually log messages that I was missing there, but we eventually got to the bottom of that. And also Fluentd still uses a lot of memory, on the order of several gigabytes per Fluentd process. So if we go back to the diagram that I had here, each of these Fluentds is using several gigabytes of memory, and of course if you want them to be highly available, then you're running multiple Fluentds for each of these Fluentd boxes in this diagram. So that's also, we can afford it, but it's also not ideal, especially when we're not processing log batches that big. We had to make various fixes, so we submitted a total of 9 patches to various open source projects in the process of this work. I won't go through all of them, but a couple of the things that we did were we added metrics to the Prometheus plugin for Fluentd to report the oldest and newest time keys in the buffer. This was before we decided to go with the new approach. We wanted more visibility into Fluentd's buffering. One thing that Fluentd lets you do is chunk buffers by time key. So you say, basically cut logs up into 10-second or 30-second or 60-second increments and write each one to a separate chunk in the buffer. And I just wanted to have metrics so we could see, okay, what's the oldest time key that we haven't yet processed, and also what's the newest time key so we know if there's some delay upstream of Fluentd. With Kafka, we of course have better ways of finding these metrics using the metrics on of the Kafka consumer group lag, but those metrics are now on the open source project, so if you're doing things the traditional way with Fluentd, you can make use of that. We also did some fixes for the way timestamps were handled, so we could use Kafka's timestamps as our canonical source of timekeeping rather than having a separate timestamp within the message, given Kafka already provides that. And we also implemented correct consumer group rebalancing, where previously, so the way a consumer group in Kafka works is you have a group of consumers that work collaboratively, and when a group is formed, each group member sends a join group message to the Kafka broker, which will wait until it receives, well, it'll wait for a timeout or until it receives a join group from all known consumers in the case of a consumer group rebalance. There was a bug in Ruby Kafka where it was using an old version of the join group message that caused the broker not to wait for a timeout. So every time a new consumer tried to join, it would end up in a consumer group of one, and all of the other consumers would be kicked out of the group. So they were fighting each other over processing the logs in serial instead of processing them in parallel as they're supposed to. So we also fixed that. So there are a bunch of improvements there that other projects can also make use of. And now there is some bad news. So I talked a bit about the fact that the Ruby Kafka plugin makes it difficult to balance nice big log batches with reasonable failure recovery times. For that reason, after this talk was submitted and it already had a title, we decided to drop Fluentd for processing log messages from Kafka. This approach in general is still possibly useful for anyone else who might want to try a deployment like this with Fluentd. But it's not all bad because we are still using Fluentd in one case. So before the logs even get to Perapera on our Kubernetes cluster, we're using Fluentd to write the Kubernetes logs into the journal. So that's what I said before. We've made an architectural decision that all logs on a node go to the journal, and that is our canonical buffer. So we use Fluentd as the way of getting logs into that buffer for Kubernetes. This is what the third iteration looks like, and this also illustrates a nice property of the design that we went with, which is that components can be replaced. So we could easily just take Fluentd out of the slots here in this diagram where it was, and put in Kafka Streams and Kafka Connect. We also switched to S3 for log archival for other reasons, but the thing here is we could still use Fluentd if we wanted to. So we could still use Fluentd for filtering and use Kafka Connect for output, or we could go the other way and use Kafka Streams for filtering and use Fluentd for output. So breaking things up with Kafka buffers in between makes it possible to independently replace each component of the architecture without needing to consider dependencies, as long as each component agrees on the protocol that gets written to the Kafka topic. Perapera didn't need any modification to deal with the fact that we replaced Fluentd with Kafka Streams. So that's the real power of this solution, and we may bring Fluentd back into it at some point. It's easy to add it back in because we can just slot it in wherever we want it. So, and the future of this, I mentioned some of the open source contributions we've made. We are looking at the possibility of open sourcing some of the new software we've written if we find that it's not too specific to our setup. Currently, I can't make any promises at all there, but we are looking at that possibility. And for updates, you can look at our GitHub org, or you can feel free to reach out to me personally if you want. And yeah, so that's about it. Are there any questions? Hello. So I'm going to go through these questions in the order that they came in. So the first one, which should be appearing now. How did you detect in Fluentd that the logs were being sent duplicated? We actually detected that in CloudWatch because we were noticing that CloudWatch had hundreds and hundreds of the same log over and over again. So that was actually tracking down where that came from did involve looking at the Fluentd logs. In the logs, it was just saying that there were partial failures running to Elasticsearch, and I actually went and looked at the Elasticsearch plugin code and eventually found that it was documented in the README and we'd missed it. But the initial way we found that was just seeing that there were duplicate logs in CloudWatch. So how did you handle misconfiguration that caused duplicates within Fluentd due to partial success requests. In the end, we handled it by completely changing the architecture, as I described in the talk. But the short-term fix is the Elasticsearch plugin will re-emit those logs with a particular label, and you can match on that label and just throw them away. If you the short-term fix was just throw them away so that they stopped being duplicated. But ideally, you're supposed to handle those re-emissions properly. This one, I'm not entirely sure what it's a difference between Fluentd, Fluentbit with Kafka integration. I assume that's asking about the difference between the two architectures. With the Fluentd forwarding protocol, Fluentbit sends log messages directly to Fluentd over a TCP connection, whereas with Kafka, well, it's still going over a TCP connection, but Kafka isn't doing anything smart with it, so it's much less likely to break. Is there a way to know, maybe looking into the code, if an output plugin does or does not support buffering? Yes, there is. At the very least, you can look at the code. There are probably other ways, but if you look at the code, there are two methods that it can implement. There's one called process and one called write. One of those is buffered and one of them is unbuffered, and I don't remember which one's which, but yes, you can easily see from looking at the code which ones it implements. This next one's a good question. How many logs can you ingest and consume with this solution? So far, it's handled all of the log volume that we've thrown at it. So I don't know what the upper limit is, but it's higher than the most logs that we've had to try to use it. I can get you better numbers if you want to ask that one again in the Slack channel after the talk. I can take a look and give you a more concrete answer to that. This next one, why don't we use Fluentd memory buffer instead of unbuffered mode? Because we want to make sure that if Fluentd crashes while something is in its buffer, it gets properly flushed. We don't lose those log messages. So what we were doing previously was using disk buffering, and we actually had that on an EBS volume attached to the instance, so that if the instance died completely, we still had that EBS volume with the buffer, so we could recover those logs. With a memory buffer, you don't even have that option. If the Fluentd process dies while there are logs in the buffer, you've just lost those logs forever. So the advantage of using unbuffered mode is that the input plugin, the Kafka input plugin won't acknowledge that it's read those messages from Kafka until the output plugin has actually written them. So it guarantees that we don't lose logs. Did we consider Apache Pulsar instead of Kafka? No, to be perfectly honest, I've never heard of Apache Pulsar before, but one of the reasons we use Kafka is that we're also using it in our application, so it made sense to use technology we were already familiar with. Is Perapera open source? No. No/not yet. As I said, I can't make any promises at the moment, but it's one of the components that we're looking at the possibility of open sourcing. Did you ever encounter missing logs in journald? I'm not sure what. So journald is kind of our canonical. That's what we treat as our canonical source of logs to export. So that's, in a way, the definition of a log message existing is going into journald. I can't say that we've ever encountered a situation where we've we found a log message that we thought should be in journald but isn't. The only thing is if journald has limited retention, so if Perapera falls behind, it can miss log messages if the journal gets rotated. But that's a matter of configuration. First of all, Perapera doesn't tend to fall behind often, and second of all, you can adjust the journal rotation if you need to. So how many people do we have on this team? It's a good question. The team's been reshuffled a bit. In terms of people actually working on this, I'd say 2 people who have worked on it in any significant capacity. Did we evaluate using FileB as log shipper? No, to be honest, I haven't. That's something I haven't heard of either. So this next one is an interesting question. What were the red flags before deciding to improve the solution during the various iterations? That's kind of a really broad question. I would say that the most important ones I described during the talk. So clearly the initial problem that led to this restructuring is a problem with the problem that was caused by Elasticsearch having problems and backing up throughout the stack. All of those issues were kind of red flags. None of them by themselves was very serious, but all put together, they kind of convinced us that we had to change something. Next question is, we show a K-stream, why not use a Fluentd source and Elasticsearch sync connector? We could do that, and we were doing that. The reason why we stopped doing that was, as I said, there are problems with the Ruby Kafka library that make it difficult to consume batches of messages effectively. You can either have really big batches and very infrequent heartbeats, so that it takes a long time to recover when something goes wrong, or really small batches and really short heartbeats, so you recover quickly if things go wrong, but you end up doing a lot of API requests to Elasticsearch, which, to be honest, in the case of Elasticsearch, was not that big of an issue. It was more CloudWatch because of its API limits, but we decided to just go with Kafka streams for everything. So this question is asking, did we have a particular config for the topics in Kafka? Currently we have 24-hour retention, which is more than enough. We always process those logs in a timely fashion. Replication factor, I think, is 3 or so. It's a fairly standard configuration. Someone is asking, can I explain what Kafka does? Well, as I said, it's a distributed messaging broker. So you essentially have one thing that writes messages to it and another thing that reads messages from it. And the whole point of Kafka is to be very reliable and distributed and fault tolerant. So there's obviously more to it than just reading and writing messages. The idea is that it should basically never go away because it can survive all kinds of failure modes. That's it in a nutshell. Any more than that, I think, is out of scope, but there is excellent documentation on the Kafka website if you want to read that. Next question is, did we think of using Flink over Fluentd when it comes to stream processing? No, I haven't heard of Flink, to be honest. I did look briefly at. I'm completely drawing a blank now. There is another tool that I looked at that I cannot remember the name of, but in the end, it was Fluentd seemed to be the thing that had all the plugins that we wanted for filtering and so forth. And I mean, it would have worked well if it hadn't been for the problems that we had reading messages from Kafka in a reasonable fashion. But in the end, Kafka Connect and Kafka Streams turned out to be I think, the best fit, partly because we're already using Kafka. We might as well use the methods Kafka provides for this stuff. And that's all the questions for now, I think. Well, thanks very much for coming. Thanks very much for all the questions. And yep, please join in the Slack channel that's on your screen now. Bye.